In this video, we will discuss boiling point elevation and freezing point depression. The concept of boiling point elevation and freezing point depression is related to entropy and the previously discussed topic of vapor pressure lowering. So for instance, for boiling point, well, if you want to boil something, you need to bring its vapor pressure to atmospheric pressure. So if you take a pure liquid and you add something and you make it a solution, well, it now has a lower vapor pressure, meaning that you have to add even more heat, thus raising the boiling point in order to get the vapor pressure to equal the atmospheric pressure. As opposed to freezing point depression, well, a pure solvent is much more ordered and less chaotic and has much less entropy than a solution. And therefore, if you have a solution, if you want to freeze it, well, there's a huge difference in entropy here. You're going to have to lower the temperature in order to freeze that solution. Now, the equations for change in boiling point, or boiling point elevation, and freezing point depression are very similar. So, for instance, the change in boiling point is equal to what's known as the Van't Hoff factor times the boiling point elevation constant times the molality of the solution. The freezing point depression, or the change in freezing point, again is equal to the Van't Hoff factor I times Kf times molality. So for example, ethylene glycol, common automobile antifreeze, is usually a solution in water. Now it's very important to note that we are talking about non-volatile solutes. This does not work when you have volatile liquids mixed with other volatile liquids. That is a completely different concept. So we have a non-volatile liquid dissolved in water. We want to calculate the new freezing point and the new boiling point of a solution that contains 685 grams of ethylene glycol and 2,075 grams of water. Well, we need to know a lot of things. We need to know the Kb specifically for water, not for ethylene glycol, and we need to know the original boiling points and melting points for water, which hopefully we already know. We're going to find the change in freezing point first. For a non-electrolyte such as ethylene glycol, the Van't Hoff factor I is just 1. So we need to find the molality. We need to know the moles of solute and the kilograms of solvent. And once we have the molality of this solution, we're just going to plug it into our equation for delta Tf. Now, this is not the new freezing point. This is the change in freezing point, and freezing point depression is always down. So, we need to subtract 9.893 from the original freezing point, and we get a new freezing point of negative 9.9. Calculation of the boiling point elevation is pretty easy at this point. We have all the information we need. All we need at this point is the Kb for water. So we plug in the Kb for water. We already know the molality. Van't Hoff factor for a non-electrolyte is 1. We get our change in boiling point, but this time we add it to the original boiling point, because this is boiling point elevation. So the new boiling point of this ethylene glycol solution in water is 102.8 degrees Celsius.